Okay, well, I have 1 o'clock Eastern time on my computer, so I think we're going to go ahead and get started with today's webinar. First, I would like to thank everyone for joining us today for our webinar on nitrate water treatment. I'm Betty Wells, and I'm the VP of Marketing for Envirogen Technologies. I would like to introduce you to today's speakers. First is Dr. Todd Webster, who carries out dual roles at Envirogen as VP of our food and beverage efforts, as well as our mining efforts. Todd has more than 20 years of experience in all aspects of biological and phys-chem treatment systems. He earned a PhD and a master's in civil environmental engineering, and also his bachelor's degree in aerospace and mechanical engineering from University of Southern California. He is also a registered professional civil engineer in the state of California. Next, I would like to introduce Paul Kita. He is responsible for business development in the Western US for Envirogen. Mr. Kita has been with Envirogen for 2 years now, and his focus is on Ionexchange systems as well as operation and maintenance services. Paul has over 10 years of experience in water treatment, waste and recycling, and odor control, and he holds a bachelor's in chemical engineering. And with that, I would like to turn it over to Paul.
Hello, everybody. Thanks, Betty, for the introductions. Just to mention one thing, if anybody has any questions throughout this presentation, on the right-hand side of the screen, there's a questions tab where you can type them in and we'll take them up at the end of the presentation. So let's jump into this. Today, we're going to be going over the understanding of nitrate water treatment. So the topics for today's presentation that we'll go over will be sources of nitrate contamination, the problem with nitrates, regulatory status, technologies used to remove nitrate, Envirogen solutions, as well as case studies. So we'll go into the nitrate contamination first. So how do nitrates end up in water? There's a couple of different ways nitrates end up in water, such as agricultural fertilization and animal waste, power plant flue gas desulfurization, municipal and industrial water discharge, mining operations, as well as NOx emissions. So the nitrate sources are composed about 80% from agricultural sources, such as contamination from crop fertilization, as well as discharge of animal waste, as well as 20% of non-agricultural sources. 6% are released from point sources, such as municipal sewage plants, and 14 are deposited from atmospheric sources, nitrogen oxide emissions. So here's a map of groundwater influenced by nitrogen in the United States. The red areas are the areas with the highest nitrate contamination, and they're correlated with agricultural parts of the US, such as the Midwest, California, and Washington. So why are nitrates a problem? The main issues with nitrates is that they cause health-related issues as well as environmental problems. Health-related issues that can be attributed to nitrates are blue baby syndrome, colorectal cancer, thyroid disease, as well as can cause birth defects and miscarriages. For our environmental problems that nitrate causes, mostly it's due to algae overgrowth in water sources, which causes the depletion of oxygen in water, causing death of organisms such as fish. So let's go into the regulation of nitrates. The U.S. Environmental Protection Agency has set a maximum contaminant level, MCL, for nitrates in public drinking water supplies of 10 parts per million as nitrate. In addition, the US EPA established National Pollution Discharge Elimination System permit requirements for nitrate also. So how do we remove nitrates from water? There is a couple different ways to do that. The technologies that are most prevalent in the industry are composed of ion exchange, reverse osmosis, electrodialysis, biological denitrification, as well as chemical denitrification. And we're going to go in a little bit more detail about each of these technologies, its pros and cons. So first, we're going to talk about ion exchange. Ion exchange is a resin-based system where an exchange of ions occurs. The advantages of this technology is there are nitrate selective resins available that are specifically designed to remove nitrate. There's a lot of common applications, and it can remove multiple contaminants. The disadvantages of this technology, there's a potential for nitrate peaking, high chemical salt use. There's brine waste that needs to be disposed of, as well as possible disinfection byproducts such as NDMA. So reverse osmosis is another technology used to remove nitrate. It's a membrane separation process where ions are removed. The advantages of this technology is it can remove multiple contaminants. It's also desalination, and it also removes TDS. The disadvantages of this technology are composed of membrane fouling. The membrane can foul and scale, lower water recovery, operational complexity. There's very high energy usage, as well as waste disposal that needs to be taken care of. Electrodialysis is another technology that we are familiar with and is used to remove nitrates. It's a membrane technology that uses electrical energy to separate ions across the membrane. The advantages of this technology is it also can remove multiple contaminants. It has a higher water recovery. It removes salts and is unaffected by silica, unlike RO. The disadvantages is the energy demands are very high. It is pretty complex to operate, as well as it also generates waste. Biological denitrification. So biological denitrification is a microbial-mediated process where nitrate is biologically converted to nitrogen gas. The advantages of this technology is it produces no waste brine. Nitrate is reduced rather than transferred to waste stream. There's a high water recovery and potential to remove multiple contaminants. The disadvantages of this technology is it requires nutrients and substrate, produces biomass, is possibly more complex and has higher monitoring needs than other technologies. It's sensitive to environmental conditions, such as flow changes and flow conditions, and there's a risk of nitrate formation. The last technology that we'll go a little bit more detail in is chemical denitrification. Chemical mediated process where nitrate is chemically reduced. The advantages of this technology is also does not produce brine or waste brine or concentrate. Nitrate reduction rather than transfer to waste stream. There's a potential for removal of multiple contaminants. Some of the disadvantages, it's inconsistent nitrate reduction, risk of nitrate formation, a reduction to ammonia, pH and temperature dependence, as well as possible need for ion removal. So how do you choose the best treatment option? So the most important thing is to gather process parameters of your waste stream that you need to treat, such as flow rate, influent water quality, system utilization availability, treatment goal versus system versus overall, as well as waste rate compared to operational costs. So, and this is where Envirogen expertise comes into play. We are very technology agnostic. We choose the best technology based on process parameters that suits our customers' needs. There's a couple different parameters here that we take into consideration based on what the customer is required and what is his availability is. And with that said, I will let Dr. Webster go into detail on Envirogen's approach to solving nitrate water contamination challenges.
Thanks. Thank you, Paul. Thank you, Paul. So what is Envirogen's approach? As Paul has mentioned, we do look at all technologies, and we have many of these technologies in our sort of a quiver available to our clients. But I'm going to focus on a couple of technologies that we've been involved in the last 25, 30 years that really are sort of the pillars you see in the industry for nitrate treatment. And certainly technologies like reverse osmosis, electrodialysis, and chemical treatment have been used, but we have focused a little more so on biological denitrification using our fluidized bed bioreactors, as well as Ionexchange technology, regenerable ion exchange. And oftentimes you can compare the two and help the client understand the best life cycle cost. So let's talk a little bit about the fluidized bed bioreactor. Again, there are many means to biologically treat nitrate. And there are moving bed bioreactors, membrane bioreactors, packed bed reactors. We focused over the last 30 years really looking at the fluidized bed reactor because of some of the advantages that we've seen with this technology. And what is it? Well, it's essentially an active fixed film bioreactor that fosters the growth of microorganisms on a hydraulically fluidized bed of specified media. And that media could be granular activated carbon, could be sand. Typically the two that we utilize, very specific medias though, and how they're implemented with density and their hardness, things like that. So not just any carbon or any sand, but it's a proprietary design that we've developed and can be used really for potable and non-potable applications. And I'll be talking about that in some of the future slides. So the FBR can be used, so when we're talking nitrate today, but as well as other contaminants or co-contaminants in the same process. For nitrate treatment, you'll use an anoxic fluidized bed reactor, but you can also, we've developed aerobic and anaerobic units to treat VOCs and other contaminants as well. But today we have more than 75 FBR units installed over, I think, 31 sites. And so the technology certainly is something that we have experience and have been able to apply in a number of applications for clients. And I want to just go in a little further to talk about how the anoxic FBR works. And this is again related to nitrate treatment. In this particular slide, we essentially there is a recirculation pump which fluidizes the media within the FBR reactor or a vessel. These vessels can be FRP, they could be stainless, different materials of construction. But that recirculation pump continually fluidizes the bed, and there's a recycle aspect of that water to the suction side of the pump. Now, if you can imagine, you start feeding in the contaminated groundwater, which has nitrate in it from the left, it feeds into that recycle line and ultimately comes into the base of the fluid bed reactor, where it then is treated by the microorganisms that live or attach on to the media. And now, in order for that process to occur, denitrification, you have to add an electron donor if there's not already one in the contaminated groundwater. And in many cases, that electron donor might be something like ethanol or acetic acid. There are many different electron donors that can be used, sugar, molasses, but that is what's oxidized, and ultimately in the oxidation reduction process of denitrification, that organics oxidized, the nitrate is reduced, and it's converted to nitrogen gas, which comes out as a gas phase out the top of the reactor. And again, as you look at the hydraulics of this unit and you see the contaminated groundwater entering the left, it's just a mass balance of what comes out the right. So if you have 1,000 GPM entering the recycle line, you'll have 1,000 coming off hydraulically the effluent. Next slide. And so some of the advantages of this type of a process, we can build very tall reactors and where footprint is critical, or minimizing footprint, should say, can operate at steady state. Again, this is a fluidized bed reactor, so it doesn't require backwashing or burping in terms of nitrogen gas that might be formed. The gas is always quiescently released out of the top of the reactor as the process occurs. It's a robust technology. Because of the media that we use and the application, and certainly the years of experience implementing, it doesn't, plug up. It's homogeneously distributed by the fluidization pump. Flexible, it can operate over a wide range of flow rates, and can treat to low levels with a smaller footprint than other traditional biotechnologies, partly because of the amount of active biomass you can get on a particle of media that's within the FBR. And so in terms of specifically denitrification, it does handle these higher flows at a lower cost, can treat 99% or greater, really down to non-detect levels of up to 500 parts per million as nitrate. And that will generate a lot of nitrogen gas, of course, and it does require that electron donor, but still these systems can be economically run and technically achieve what the client needs for effluent. We do have existing systems treating anywhere from 5 gallons per minute up to 6,000 gallons per minute. At the end, I'll give a few case studies to demonstrate that. And to be clear, again, denitrification involves converting the nitrate to nitrogen gas. And so it's no longer an issue. It's not like a phase transfer in a biological process, or say an adsorptive process where you're just moving nitrate from the liquid phase onto a solid. And so in this case, it's completely converted to nitrogen gas. And it can be implemented, the technology, as a standalone unit or integrated into an existing treatment system. So if a client or yourselves, you have an existing plant but have now a nitrate treatment need, it can certainly be integrated into that process stream. And one of the things that we have strived with this particular technology is to make it modular, packaged FBR design where applicable. And this is oftentimes implemented for sites that might be more remote or have limited accessibility at the site. And it helps to reduce the overall installation costs by modularizing this. And it allows us to minimize that site engineering, the on-site cost, and streamline the installation a little more if you can have more of a plug and play type of a system. And so this is something that is available. You see in some of the case studies, larger examples of the FBR technology I'll show you. But in this case, for maybe a little smaller flows, this might be a suitable alternative to have a packaged type of plant. Now, and with the biological denitrification, I mentioned earlier that you're converting that to nitrogen gas. We also look, though, at ion exchange, regenerable ion exchange as a possibility with our clients. Again, trying to offer our clients the availability or our knowledge base to implement really the technology with the best life cycle costs. And for us, whether it's ion exchange makes more sense, or a biological treatment, or even RO or electrodialysis, we can look at all those, as Paul mentioned earlier, being agnostic about it, but just trying to help the client with the right technology for their particular application. And for ion exchange, what is ion exchange technology? Well, it's a physical chemical process where ions are really transferred from the liquid phase we're talking about here, nitrate, onto a solid medium. And it's a chemical potential process. So charged surface attracts a negatively charged surface, will attack a positive ion. Next. And just to give you a little bit more of a understanding of the process as it relates to nitrate, you'll have a resin within a vessel, and you'll have a nitrate molecule coming in with the incoming feed water. And on that resin is a chloride ion. And based on these chemical potentials, really the nitrate will essentially knock the chloride ion off and be more attracted to that resin. And so then what comes out in your effluent is the chloride ion, and the nitrate has now been removed from the water and is attracted onto the media or the resin. However, you can see that it is a reversible process. And that's the idea behind regenerable ion exchange. versus say single pass. You can do single pass, no doubt, and just remove and replace the resin after you've reached capacity. But with nitrate having generally ppm levels coming in, that would mean you'd be changing out resin quite frequently based on the loads. The regenerable aspect allows you to add a higher level or higher concentration of brine through the process, through the vessel, and that higher concentration of brine and that chloride ion will knock the nitrate back off into the waste brine. So it is a reversible process that that we've been able to employ as a regenerable ion exchange technology. And so this is what we're talking about in terms of our proprietary high efficiency regenerable process. What the key here is that for all of our clients, we're really trying to minimize the amount of waste that's developed, the amount of salt that's utilized in that regeneration process, and of course meet the effluent goal for the nitrate that's coming in. And how do we do this? With our one of our technologies for a little bit larger flows is called the Simpac Design. And essentially, as I mentioned, to minimize that salt consumption and the waste production, the Simpac Design uses multiple smaller vessels, all operated in parallel. And with this design, the effluent from each vessel is collected and manifolded together such that the effluent nitrate objective can be met. The idea with this approach is a fraction or a portion of the vessels that are in service can be overrun completely with nitrate and then blended internally out by the effluent of the other vessels. So unlike a lead lag system where you're just running water through one lead system and then into the lag unit, not all of that resin bed is utilized as you start to see breakthrough. But by allowing us to run multiple smaller vessels working in concert, we can overrun some of the beds completely, but using the other balance of vessels that are in operation and manifolding the effluent to dilute to whatever level of nitrate treatment we want to achieve. And this gets us to allows us to use all that capacity within those beds. Well, what does that mean? It means that we don't have to regenerate as frequently. And when we do regenerate, because of the less frequency, we don't have to use as much salt overall. And so we reduce the salt consumption, but we also reduce the waste volume that's produced. And it allows us to have very low waste rate and volumes for the client to have to ultimately discharge or to ship off site. And finally, we also employ sort of a cascading aspect of our regeneration process, which allows us to actually reuse some of the brine and the rinse water within pairs of vessels. And that also contributes or allows us to minimize even further the waste volume that's utilized. So all of these aspects are based on some modeling and that we are capable of conducting, but also years of experience and how to operate these types of regenerable systems. And, mentioning the Simpac Design for nitrates, certainly it's utilized in that aspect. It can also be used, Ionexchange technologies can be used for arsenic removal, radium, barium, perchlorate. And typically these applications for this technology are greater than 500 GPM. And really looking for clients who are maybe don't have a good place to release their waste volume, or they have to ship off site. Therefore, they're really trying to minimize whatever waste volume is produced. And you can see in this couple photos here, it can be in a Connex box packaged, a shipping container, or it can be placed into a building in various configurations. And then a smaller version of this is what we call the Minex ion exchange system. And it's used for flows very low GPM to 350 to 400 gallon per minute flow rates. With the lower flow rate is it's less capital intensive. There's less vessels that are put into place with the MinX design. And because there's less vessels, though, might imagine that it'll basically, it doesn't allow you to dilute out with more vessels, and therefore there's a little bit higher wasting rate that is seen with the MinX design versus the Simpac design, just inherent in the number of vessels that are operated. But the capital costs certainly are lower, and it should be, because we're looking at lower flow rates. And so I'd like to move into some case studies that just to show you sort of the breadth of experience with these technologies. And again, whether it's Ionexchange or it's the biological fluidized bed reactor, what makes sense for nitrate treatment for the client? And that's really what's critical here. With the FBR, we've been able to show with a number of installations and a number of major companies like Tech Resources, our Kinder Morgan, major energy company, this technology being implemented at large full-scale levels for nitrate treatment. And one of our oldest installations is a specific case study is the Aerojet facility up in Rancho Cordova treating nitrate. It is also treating perchlorate biologically. It's up to a 6,000 gallon per minute flow rate using multiple 14-foot diameter, in this case, stainless steel reactors, and ethanol is being used as the electron donor. Again, for purposes of how many years, this system's been operating for now 22, 23 years. And although the technology has, we've made modifications and improvements over that time period, certainly the fundamental basis has always stayed the same. And like anything, we continue to strive to find technological improvements and advances to minimize the size of these systems as best possible. Another example of the fluidized bed reactor technology implemented is in Henderson, Nevada. This is the largest nitrate perchlorate chlorate treatment facility in the world, and essentially treating about 1,000 GPM with multiple reactors, very high concentrations, hundreds of parts per million of all of those contaminants, but certainly the nitrate levels in that range, and essentially producing non-detect water for both nitrate and perchlorate, and it's feeding the Las Vegas Wash, which is part of the Lake Mead system and that feeds the Colorado River. And so this water that's being produced at this particular facility, and this is right outside Las Vegas, Nevada, ultimately feeds potable water to millions of customers in Southern California through a metropolitan water district. Now, the last example is an example of indirect potable water treatment, but a direct potable water plant was built in 2016 at West Valley Water District, treating nitrate and also the other oxyanion perchlorate. It's a 2,000 GPM system, and treating nitrate and perchlorate levels to non-detect, and going through the fluidized bed reactor, then followed by a filtration and chlorination step to be able to make that water potable. So in that case, it's directly then released to a reservoir, which is pumped to the residents of the city of Rialto for consumption. And this was the first plant in California for the treatment of nitrate and perchlorate permitted. And ultimately, it's now been running for 5 years, and it's been a very big success. So that touches upon just a little bit for everyone, the FBR technology for both industrial and potable applications. But for the Ionexchange technology, we have also implemented that both within municipalities and within industry. And here's just an example. Many of these sites are located throughout California. And you can imagine, because California, really the West, has so many groundwater resources that it utilizes. And so But really throughout the state, we have implemented, in California and Arizona, we've implemented the technology, and it's been permitted by at the time, the Department of Public Health in California, now the regional board. And just a couple of case study examples. High Desert Water District. This is a particular system in a building. You see some reservoir tanks there, but the building to the right where we've implemented the technology, it's treating 2,500 gallons per minute. And the nitrate coming in is about 58 and leaving at 20. And again, the MCL is 45 for, or 45 milligrams as nitrate, or 10 parts per million as nitrate nitrogen. The units here are 20 ppm of nitrate coming out. So well below the MCL, getting the treatment level, and really very low waste rates, and therefore the discharge costs are very minimal. Another example is the city of Pomona. This one is treating a population about 150,000. And when implementing the technology, looked at it, that it had 90% less brine waste produced compared to the conventional Ionexchange that they had been using prior. And then ultimately, you can see here is a Connex box. It's a shipping container where the system is built inside. And what's nice about it, again, is it can be plug and play. You can put a concrete pad down and just need a contractor to bring in the electrical and the influent, effluent plumbing or conveyance water to the system. So it allows for rapid installation, and then ultimately, with the number of systems we've permitted prior, the state can permit fairly quickly. This is an industrial example of where the technology's been employed. It's a large winery on the West Coast. This is a particular client wanted to use regenerable Ionexchange technology really as a fireman, which serves nicely to do so. When they needed water, they wanted to be able to run the system. And during the drought in California, it was critical to have this as a potential resource. They don't use it all the time, but when they do use it, the waste rate here, very low, approximately 0.3%. Was their wasting rate, and their untreated water coming in at about 80 parts per million, so well above the MCL at 45, and treating down to 16 parts per million as nitrate. And ultimately, again, using this as a fireman, but they're wanting to use in their process of producing wine and washing tanks, washing fermentation tanks. And really just being their potable water source as needed. And then lastly, just to give you that example of a couple more systems, another 1,000 GPM system in California and another 2,000 system in California. But just emphasizing that the shipping container modularization of this type of technology versus also the ability to lay it out in buildings as necessary. So it really is up to how the client wants to install the technology for various reasons. And with that slide, in conclusion, Envirogen looks at nitrate treatment, looks at the various technologies that are available, and really tries to understand the capital and operating cost for any and all of them, and then utilize that to help guide our clients for what makes the most sense. I focused today on biological with the FBR and regenerable Ionexchange. Again, as I stated earlier, these are sort of the pillars in industry right now that are accepted. There are other technologies, and there are continually emerging technologies, and we strive as a company to endeavor to continue to stay on that cutting edge, reviewing those technologies, and if they make sense, that's what's implemented. But with that, for Paul and I, and for Betty, I thank you for attending, and certainly we're open for questions about any aspects of nitrate treatment or any specific case studies that we may have shown you here today.
So we did have one question regarding, will the slides be available after the presentation? And the answer to that is yes. It'll be available through Livestorm, but that will have kind of that dead space at the beginning before we got started. I'll also put a clean version out on our website, which will also be on the Envirogen YouTube channel. So anyone who wants to review this whole presentation with the speakers' commentaries can do so. Also, if you have any questions for us now, feel free to type them in to the questions tab on the right. Or if you'd rather have a private conversation, you have Paul and Todd's email addresses here on the screen. Feel free to reach out to them independently at when it suits you. Any other questions today? I guess not. So again, thank you, Todd and Paul, for delivering the presentation today. And thank you very much for all of our attendees. We hope we can help you out when you have future needs for nitrate treatment or any other water or wastewater treatment. So thank you again for attending.